Hello there, I'm Sina. I'm here to explain my research at Polito. My research is focused on fine-grained image analysis. In this presentation, I'm going to talk about applying AI on medical images. Deep neural networks require tremendous amount of data to be trained, and we are trying to reduce that amount. But why? And how? Now, let's start with why. First of all, on the contrary to usual everyday images, the acquisition method itself is costly, since it requires high-end devices, and, usually, not usable by everyone for privacy matters. So in most cases you are bounded to use publicly available datasets for training. Then it comes to the concepts that the deep neural network should learn. For diagnosis purposes, supervised learning algorithms also require the ground truth for each image in order to be trained. To make the ground truth, for each case several experts need to reach a conclusion for an accurate decision. Therefore, making the ground truth becomes time-consuming and expensive. In short, even if we have enough number of images to train a supervised deep neural network, the annotated data may be limited. In such cases, practitioners use a previously trained network which helps the network learn faster by relying on what it has learned before. However, the domain gap between the pre-trained network and the medical field is high, because the pre-trained network has been trained on normal images, not medical ones. But what if there was a way to close this gap for different types of medical image acquisition such as MRI, CT scan, and X-ray? And that's exactly what we are trying to do. We are creating modules that tries to close the aforementioned gap between the pre-trained network and the final task, reducing the need for relying on annotated data, and also able to adapt to various modalities and tasks. This will reduce the costs of annotation as well as simplifying development of models for specific tasks such as computer-aided detection, which helps radiologists to save time, and improves diagnosis quality. To illustrate, let's visualize the images in a 2D space and see what a bad representation of the data looks like. Here, you can see an example of a bad representation. Not only the modalities are not distinguished, but also the body parts are not understood by the network. Instead of starting with a representation like this, where all of the images are mixed, we can start with a network which already has an understanding of the medical images and distinguishes them. As you can see, the images on the left are distinguished by modality, and images referring to one modality are clustered together. On the right, you can see the same representation also has an understanding of the body parts. In this example project, we have created a comprehensive dataset to cover various modalities and body parts. To avoid using the ground truth labels, we have utilized a technique called self-supervised learning, meaning that the network has been trained on an auxiliary task to learn the context, texture, and appearance of the images. This is an ongoing project. We are trying to further enhance the representations for diagnostic purposes. Some of the other research activities in our group, related to the medical domain, are shown on the screen. I would love to share them with you, but, unfortunately, time won't permit. Please feel free to contact us for more information and details. Our research group is called GRAINS. I'm Sina Famouri. I work with Leonora and my supervisor is Professor Fabrizio Lombardi. You can contact us via email or through the group's website. Thank you for your attention.